All right. Well, welcome everyone to the ArduPilot systems update for 2020. So this is where I give an update on all of the sort of low-level device driver, RTOS, board support, etc., that's been going on in the last year. And it has been a very active year. We've had over 5,000 patches merged into master, which represents a lot of work by a huge number of people. Over 150 people contributed patches into the master in the last year. And in total, about 500,000 lines of code has changed in master in the last year. Some of that's sort of rearrangement, but there's an awful lot of new code that's gone in there as well. We're also getting very active people sort of looking at us on the community. You can see there sort of 46,000 views of our GitHub repository and 7,000 unique visitors happening in the last month. So what's been happening? Key changes at the Shibios HAL layer. As you know, we use Shibios as our real-time operating system in ArduPilot and as the primary one for the STM32 based boards. We've done the final phase out of NutX, so that's been a 2-year process. And so the last stable releases that are based around NutX have been removed. So now all of our stable releases and of course the beta and latest bleeding edge releases are all based around Shibios. The H7 support, which is the new STM32 H743 that I introduced in my talk last year, that's now supported in all of our stable releases, which is a really huge advance, massive amounts of improvement in CPU and memory that's available, which opens up all sorts of new possibilities. We have a whole bunch more flight controllers that are now supported. I've just given a list there of the ones that have been added since March last year. And you can see that there's a whole lot of new boards come in from many vendors. So I've been delighted by the number of vendors who've been able to send in PRs to add their new boards just by using our new HWDEF system. So sensor configuration has changed considerably, also configurably, since last year. This is something that I've wanted to get done for a while and finally delighted to get this in. So previously, the way we did sensor configuration is we had if-defs all over the code. So we would have a define somewhere that says that, when we want to use the HMC 5843 connected via an MPU 6000 bridge. And so we have that, if-def, then we add that back end. So basically we have if-defs all over the code. And it was really a spaghetti code for configuring all the different boards. So this little snippet here is just for a few different possible compasses, and this doesn't cover the equivalent spaghetti code for inertial sensor, for baro, etc. The new system is what we've got down the bottom here, which is now in the hwdef.dat, which is the board-specific configuration file. We now just have one line to say what IMU we have, or we can have multiple lines for multiple IMUs. We have a line there to say what baro we've got. We have a line to say what compass. And the compiler, the HWDEF compiler, then sorts all of that out and turns it into the appropriate configuration, which basically means we no longer need the per board if-defs sitting around in all of the different driver backends. And that's a great relief. It means that patches don't conflict as much, and it means that we really just have the one file to define a board, rather than have to scatter the if-defs all over the code. We've had a big change in the way we handle USB IDs in the last year. We were using the generic STM32 ID from ST previously. That was the default one used by Shibios. And we've now completely switched across to using ArduPilot specific IDs. This gives a much better user experience. And so the new user experience, you can see little snapshots there from Mission Planner. And so when you connect with Mission Planner, you now see the USB ports showing up as, ArduPilot Mavlink and ArduPilot SLCAN. The SLCAN ones are for CAN configuration to allow you to connect to the board using we have 2 USB endpoints on one port, one for CAN bus configuration, the other for Mavlink, which is extremely useful. and people were getting very confused, getting them mixed up when they were both just called STM32 endpoints. So now we've got the specific drivers. It's really clear which one you should connect to. And on the right there, you can see a custom one for a particular vendor. That's the Hex Cube Orange, and it shows up as the Cube Orange Mavlink and Cube Orange SLCAN. And this basically just improves the user experience so they know what device they should be connecting to, particularly under Windows.
Tridge,
Yep.
does this include the bootloader?
Yes, that's right. So if while you're booting, it'll show up as ArduPilot bootloader. So it's very clear that you shouldn't be connecting to that one with Mavlink, and you got to wait for it to finish booting. So yes, the bootloader has, it shows up as the bootloader in the little drop-down box in the ground station. So that's all switched across. There's a link here to a document that is explaining all the new USB IDs. So feel free to, off the slides, just follow that link into the wiki. Thank you very much for Henry for helping us document those IDs. All right, this is another one that I've wanted to do for ages, and I described last year, but finally got it implemented just in the last few months. And this is reconfigurable hardware at runtime. And this basically arose from people wanting to be able to configure a single board, a single firmware, where they might want to change a pin from being I2C to being a UART to being a timer without having to rebuild the firmware and change the setup. And previously that wasn't possible. You could do, you know, we do have 1,000 parameters already, which you could do all sorts of configuration like baud rates, and you could turn on things like flow control, but you couldn't change the fundamental purpose of a pin previously. And so I wanted to be able to do that because it's quite common, particularly on the smaller boards, to want to be able to reconfigure a pin. So something like a Pix Racer, for example, a Pix Racer has, if I've got, I don't know, if I've got a Pix Racer here somewhere to show. Anyway, a Pix Racer has a, yeah, I've got one sitting over here, has a nice little, so there's a Pix Racer. It's got this nice little connector, which is normally used for connecting a Wi-Fi radio. But in this case, I've got the Pix Racer connected to an SPI bus connected to this fancy IMU. And so being able to reconfigure that Wi-Fi radio connector from being a UART to being an SPI bus is extremely handy. And so we can now do that type of thing just by using baud alt config. So there's a new parameter, and this is just an enum, so it's an integer value, and you can select alternate configurations for your hardware. You set the parameter, you reboot, and you now have reconfigured with a different configuration for those pins. The way you do it, you can see down the bottom here that we're switching pin PB3 on a particular board. This was on a Matex 765 wing board. And so PB3 is normally a UART 7 receive pin, but it's nice to be able to reconfigure it in case you, for example, want to use that for PPM input. And you can just put in this second line in the HWDEF. And the key part is this Alt1 at the end of the line. And that says that this line applies when baud alt config is set to 1, and the line for the same pin is then disabled, and this one is enabled at runtime. We've only got half a dozen uses of that in the tree so far, but it is a very useful thing. And particularly as people have very small boards that only have a few connectors on them, being able to reconfigure those connectors to be the purpose you want for it without having to recompile the firmware is extremely useful. I should say that, by the way, that questions during the talk are most welcome. I don't mind at all things moving around a little bit and going off into side topics. All right, the AP vehicle refactor. This was another huge change that was made just in the last few months. And this is something that, again, we've been discussing for several years, but we finally got done. And this is basically to create a parent class for all of our vehicles. So we now, so for example, copter, plane, rover, antenna tracker are now all subclasses of the parent AP vehicle class in C++. And this basically allows us to continue the work we've been doing to move more code into common code. which means that it just makes it much easier to add features that that then are immediately available on all the boards. Because we've quite commonly had a problem in the past where somebody's working, for example, on their own vehicle, which is a copter, and they add a feature that they put it only into, enable it only in the copter code, and then somebody else has to come along and do patches for plane and rover and antenna tracker, etc., to enable that. Now you can do it in one place and it's immediately enabled in all vehicle types. So as an example here, the scheduler tasks for AP vehicle. We can see that we've currently got 3 of those. They're all put in there by Andy. So this was originally inspired by Andy Piper's work to do at the runcam. The scheduler table at least was. Peter Barker did all of the work to refactor our code to allow for AP vehicle. And then Andy started using it for the runcam support and for the gyro FFT, which is the work for the real-time FFT, to be able to do notch filters that are where the central frequency of the notch filter is automatically fed off a real-time FFT on the board. CAN updates. So we had a huge amount of work on CAN in the last year. And so we've got new CAN protocols. A really big one was Piccolo CAN. And that was a great contribution by the people down in Tassie and the Kookaburra people. And so then we have Toshiba CAN as well for Toshiba CAN ESCs. The Piccolo is particularly interesting because it's a whole nother ecosystem of CAN, a bit like UAV CAN, where it's got a code generator from defining all the message types. So there's a compiler that compiles up all the different message types and builds that in. And Piccolo is particularly used in a lot of very high-end UAVs. And so it was really appreciated, that work, to bring support for Piccolo CAN in, which enables the use of a whole bunch of Piccolo CAN based peripherals that have had a very good reputation for reliability in high-end UAVs. A big step, I thought, was the HERE flow. That basically made optical flow much more accessible to a wider number of people, because previously we had flow sensors that could only be connected on SPI, and then we had sort of a low-end flow sensor that would be connected on serial. But the HERE flow is basically a plug-and-play flow sensor, very, very neatly packaged with the gyro, and very small sensor that you can attach onto the bottom of pretty much any vehicle and get really good flow performance with a short-range rangefinder. So kudos to Hex for bringing that out. The dual USB support for EasySL CAN, that was a really nice piece of work by Sid. And that basically makes it extremely easy to attach a CAN analyzer, CAN sniffer, onto a board, any of the F7 or H7 based boards, which can support dual endpoint USB. So on the one USB cable, you can connect both Mavlink and your CAN analyzer at the same time, which is great for configuration of your CAN devices and also for upgrade of the CAN firmware on your devices, which is really essential because it's common that CAN devices have onboard firmware which can be quite complex and may need bug fixes and updates over time. And this gives us a really easy way for people to do that without buying a specialty adapter. We now support RTK on UAV CAN, and so that means if you've got an RTK GPS that can be connected via UAV CAN. We've got another next step on that is to support moving baseline RTK and UAV CAN. That's a work in progress. It is working in a test branch, but not quite in master just yet. The new UAV CAN DNA system is extremely important. That's another huge piece of work by Sid. And the key feature of that is it means we support dynamic node allocation. That's what DNA stands for. So DNA is now supported without need for a micro SD card. And that's really important, that the database persists even if you change your micro SD card, or if you're flying without a micro SD card. That means all of your devices get consistent node allocation, node ID allocation, and that's really important, particularly for things like compass ordering and ordering of other sensor types. So greatly appreciate the work that Sid did in bringing the new DNA system in. Along with that, we got a really good CAN user interface in Mission Planner. Many thanks to Michael Oborn for the work that he did there, and firmware update, parameter, and monitoring of messages. It's a really user-friendly CAN user interface, and that's made CAN usability for the vast majority of our users, vastly better. So really, I think 2019 up to now is really the year of CAN development, where we've seen a massive update in our CAN infrastructure. And what I'm hoping is that this next year is going to be the year of CAN users, where we see a larger and larger proportion of our user base starting to use CAN-based devices. The CAN development will still keep going, but I'm expecting that it'll be, slower in terms of new development of core features, because we've got all of the core features now set up. And what I'm hoping now is we just start getting a larger user base. So AP Periph has been another big thing in the last year. I introduced the concept of AP Periph at the talk last year, and that's basically ArduPilot, the ArduPilot firmware running on a peripheral. So that allows you to have tiny devices, and I've got a little AP Periph. You can see one of the devices here, how small it is. That's a little AP Periph node from MRO, and really small little device. Beautiful node for prototyping and for adding, existing sensors. We've also got a new GPS, and you can see that one there. I don't know whether I've got the device on my desk to show. Yes, I do. So this is a new GPS from CUAV, which is really, really nice to see this sort of, packaged device coming out based on ArduPilot, the AP Periph firmware. So that's basically running all of the normal ArduPilot device drivers, but packaged inside a peripheral instead of inside a flight controller. And CUAV did a really nice job on making that device. So we now support in AP Periph GPS, mag, baro, airspeed, ADSB, LEDs, various type of LEDs, rangefinder, buzzer, switches, Hobbywing ESC, all of those types of features supported. And with the F303 based CAN nodes, we now can do one universal firmware supporting all of those features, where you can enable and disable each of those features just using CAN parameters. So connect in with the Mission Planner CAN interface, fetch the parameters off the node, and then you can enable and disable each of those features for a really good universal CAN adapter. So customization is the other thing that's happened with AP Periph, where AP Periph makes it extremely easy to create a new peripheral very quickly. And there's a couple of those that I'll highlight over the last year. The Hobbywing ESC adapter was one that Mananet requested from me, where they wanted to be able to decode the Hobbywing telemetry protocol from the high-end Hobbywing ESCs. And in a few hours, I was able to take one of the F303 CAN nodes from MRO and add the protocol decoding. And then we had a ESC adapter that turned a Hobbywing ESC effectively into a CAN ESC, where all of the telemetry data coming from the ESC was then shipped over CAN as CAN status messages, and extremely useful capability. The hardpoint trigger was another one that I worked with MRO on that, and they wanted to be able to take a PWM input trigger and turn that into a CAN hardpoint message. So question, Lucas.
Yes, so I have a question. What's the current flash that you need for this board, for the AP Periph?
So the minimum amount of flash we need for an AP Periph firmware is 128K. So the little F103 runs in 128K, but I do recommend the F303 based boards. They're actually basically the same price, and they give you twice the amount of flash, and they give you a lot more CPU and also a lot more DMA flexibility. So MRO has really switched across to the F303 based ones. It also means we can, with the F103, we can choose a subset. We can do, for example, GPS, MAG, and Barrow, or we can do, say, for example, AirDSB and ADSB in one node. With the F303 based board, we can have all of the features enabled in a single firmware and then just turn on and off the features with a parameter. That's a lot more convenient for end users. So if you're designing a new one, I'd recommend basing it on at least an F303. All right, so moving past, the next one is the one that I'm most excited about recently. I tend to get excited about sort of low-level system things. And this is the AP file system VFS abstraction. So we've had an AP file system for 6 months or so, and that was basically added at the point we started adding Lua scripting, where we wanted a nice abstraction out for file system calls that worked across our different HALs, so HAL Linux, HAL CITL, HAL Shibios. So this VFS system takes it a step further, and it allows us to have a virtual file system layer. And that basically gives, to allow to have memory-backed and device-backed file systems, which means you can have access to your SD card for normal files that are just sitting on a micro SD card, but you can also present other aspects, bulk data aspects of ArduPilot as files, which means they can be fetched by the ground station using the Mavlink FTP protocol. And I'm going to demonstrate 3 different virtual file systems today. One of them is ROMFS, the next one is the parameter file system, and third is the system file system. And then we can briefly discuss one that I've got planned, which is a mission file system. And these file systems are all prefixed with a magic @ symbol. So that's just to separate out the namespace. So all of the ROMFS files start with @ROMFS/, the parameter files @param/, and system files with @sys/. All right, so ROMFS file system. So we've actually had ROMFS in ArduPilot for a couple of years now, and we've mostly used it to hold a copy of the bootloader binary and fonts for our on-screen display and a few other things like that. But previously it was only accessible through an internal API. So for example, the OSD can go and ask ROMFS to give me a list of available fonts and to load the third font to be able to have runtime selection of fonts. Same when we're loading a bootloader, it can go and the bootloader update subsystem can go and ask for a copy of the bootloader.bin from ROMFS. So what this does now is this allows users to add files into ROMFS more easily. And the way you do that is you just create a subdirectory called scripts inside the HWDEF directory for your board. So some of you may know that when you're creating a board in ArduPilot, you might have a subdirectory, libraries, AP, HAL, Shibios, HWDEF, and these are all the different flight controllers that we support now. And if I go to one of the more widely used ones like QBlack, then there is a set of defaults in there. There's a HWDEF for the main firmware. There's the HWDEF bootloader, the BL1, which is for your bootloader, a README for documentation, and now I've got this additional scripts subdirectory. And so the scripts subdirectory, if you create that and you populate it with whatever scripts you want, then those automatically get embedded as part of the build system into ROMFS and are available as a script subdirectory in the ROMFS. So the big advantage of this is that all of the files are in flash rather than on the micro SD card. And that means we can put mission critical scripts inside the firmware. And they're always going to be available because they're built into the flash. So they're in the same location as our main firmware. And that means that vendors can embed mission critical fail-safe scripts or special behavior or control of onboard lights, etc., into ROMFS, and they know that if either the micro SD card fails or the user changes the micro SD card, that those scripts are still going to be available. And that's really quite critical for moving to the stage of our Lua scripts, which Michael's going to talk about in a special talk on Lua scripting later in the day, moving to using those scripts for mission critical applications. All of the files are also compressed just using gzip-9 inside ROMFS, which means they take up very little space. The Lua scripts tend to compress extremely well. So I've got an example of this little script here, which is in the test.lua. I'm going to show you how that's being used here. So I'm now connected up to a flight controller. In this particular case, I'm connected to a cube black, and I'm going to do an FTP list in the ROMFS scripts directory. And we see that there is a test.lua that has been automatically embedded in the ROMFS scripts directory. And I can get, let's see, let's just go and get that file. If I go get that /test.lua, I'll just get it to minus, and you can see that just fetches it to standard output to display it. And you can see this script is activated based on a PWM input. So that triggers when RC7 goes above 1600. So if I go RC7 1700, then you will see that you start to get these little messages coming out here. They're very boring little messages, just saying the RC level and a timestamp. And so that script is being activated when I raise that RC channel. So that's just an example of a script, a very simple script that's built into ROMFS. You can, of course, have several scripts. It also opens up the possibility of libraries. We can have libraries of Lua scripts once we support the require directive in Lua. And that will really help establishing the ecosystem of Lua scripts. All right, so that's enough on ROMFS. So,
hey, Tridge, are you taking questions in the middle? Or?
Yes, I am, certainly.
Sorry, I was just wondering, I just wanted to confirm that it's, of course, not possible to map FTP into ROMFS, right? So you can
that's
have
right.
FTP
Flash
out,
is not
in.
writable. That's right,
Yeah.
that's right. We could have a RAMFS where you could map FTP into it if we wanted to, but really people, if they're going to be pushing it to the board, they really should be using an SD card.
Cool, thank you very much.
I like the idea that you can put the scripts in the ROMFS. However, I'm thinking if you start putting lots of scripts in there, then you kind of just fill it all up. What's the possibility if we had something in the bootloader that could, this was, I guess it'll blow the 16K, but I'm just wondering if, well, maybe not. Maybe if we could give the application the binary, and the application would know that it contains the Lua script. Like it basically parse it before it tosses it to the bootloader, and then it could just forward stuff to the SD card, like the scripts.
Yeah, but we want to remove the dependence on the SD card. The scripts tend to be a lot more compact in terms of the Flash usage than the equivalent C++ code. So scripts are in fact a very efficient way of putting a feature, because a compressed Lua script in terms of Flash usage would typically be several times smaller than the equivalent C++ code once compiled into Flash.
But we are supporting putting scripts in the SD card eventually, right?
Oh yes, we support both. So it automatically looks for the scripts on the SD card in the scripts directory, APM scripts. That we've had that ever since scripting first started. The new feature I'm showing here is to also be able to have them on the ROMFS, so it supports both.
Yeah, what I'm thinking is something like the uploader Python script be able to just push those in when you compile somehow.
Yeah, Randy asked about doing it with APJ tool to add it to the existing APJ file, and we could support that.
Okay.
And that would be very similar to the way we can embed default parameters using APJ tool. And I'm guessing this is mostly going to be used by vendors who want to create a vehicle-specific firmware, and they would be doing a specific build with a different default stop param and the scripts directory. But yeah, we definitely could support a APJ tool type mechanism.
It almost feels like it's an easier scripting method to just shove scripts into it. If you want to just change something, upload it, change something, upload it.
Yeah, in some ways,
like
as long as you're willing to pay the cost of, waiting for the firmware upload, which takes about a minute or so, that slows down your development cycle. Mostly I do development in CITL.
Well, no, what I mean is have it in the uploader where it can check the let's say it could check the binary and says, oh, it matches, move on. And like the next step is we'll check the SD card. Are the files that we want there
Yeah.
already there?
Yeah, the problem with the uploader doing it is it has to be a fixed chunk of flash. Like we'd have to reserve, say, 8K or 16K, because we can't vary that, because you can't change the layout of the symbols, which means that
Well, no, but the
it's,
uploader script can actually be talking to the application as well.
yeah, but it can't relink the application. Anyway, that's we could talk about sort of the APJ type thing and uploading maybe at a separate discussion, but for the moment, I think this will be a very useful technique. All right, so moving on to the next one, which is a parameter file system. And this is, again, one that I've wanted to do for ages and really finally got around to it, pushed on by giving this talk. And I've been frustrated by how long it takes to download parameters in ArduPilot, particularly over radio links, but even over USB, it's frustratingly slow. And because the actual amount of data involved in downloading 1,000 parameters is quite small, but because the way the protocol works with the number of round trips it has and the latency involved, downloading parameters has always been very slow. At least I've found it frustratingly slow. But I must say that Michael O'Born's UI improvements with the background download are a big improvement in the latest version of Mission Planner. But anyway, this is a new way of doing it, which is basically it creates a virtual file system inside the ArduPilot firmware, which is prefixed with @param and allows the ground station to download all of the parameters as a single file, as a packed file. And so the file name is @param.pck for no particular good reason. And speed-wise, it's about 30 times faster than using the existing parameter download system on USB. On a 57K radio, it's about 4 times faster. On a 115 kilobaud SIK radio, it's about 6 or 7 times faster. So it is an awful lot faster. It uses a packed format, which packs down to about 9 bytes per parameters. Those of you know, our parameters are 16, maximum of 16 characters, name, plus maximum 4 byte of data, plus the type. So, so that means actually 21 bytes of base data, but the packing format does a type of run length encoding that averages about 9 bytes per parameter. And then there's a little script at the moment which unpacks it, and we're going to need integration at the ground station. So I'll just demonstrate that.
It has integration as of today.
Oh, well done. Oh, fantastic. Okay, so what I've got here, first of all, I'll demonstrate. I've got connected to a QBlack, and I've got 2 links. So I've got link on USB, and I've got a link on a 50 or 64 kilobaud RFD 900 modem. So I'll just do a normal param fetch over USB. And so there it's doing, you can see up here, the number of parameters counting as it slowly gets them across USB. Count, 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 slowly getting. This is our old parameter fetch mechanism, right? Running as fast as it can on USB. And there it is, and it took 14.0 seconds to fetch them on a USB link on a QBlack. It is faster on QBorange, but still it's like 7 or 8 seconds. So now what I'm going to do is I'm going to fetch exactly the same data, but I'm going to fetch it using the parameter file system using FTP. And that took 0.41 of a second to fetch exactly the same data. And what I can do now is unpack that data. There is the unpacked data. So it's exactly the same parameters, but fetched instead of in 14 seconds, down in 0.4 of a second. So really a huge difference. What I'm going to do now is set link to number 2 and demonstrate the same thing, but over the RFD 900 modem, and it's going to take it a little bit longer. So 3.5 seconds in that case on a 64K RFD 900 modem. Now I should say, by the way, that when I first implemented this, it took about 60 seconds over an RFD 900 modem to download those, a 64 kilobit one, download these parameters. It turns out that the details, the fine details of the pipelining in the FTP protocol is absolutely critical. So I put a lot of effort in over the last few days to improve the MavProxy FTP client. And I really need to write up the tricks and tips involved in that, in in getting the maximum speed for filling in gaps and handling lost packets. I also had to make a tiny tweak to the FTP protocol to allow the FTP client to specify the block size for the burst download, because large blocks on these SIK modems really don't perform well. And so it brought it down from about 60 seconds when I first implemented it down to about 3 seconds, and on a 128 kilobit link down to about 1.5 to or 1.8 seconds or so. All right, so that's our new parameter download, and thank you very much, Michael. I was hoping you might jump on that and implement that. It'd be really cool to be able to fetch those really rapidly in Mission Planner. Thank you so much. Yes.
Is there any is there any chance this will improve data flash log downloads as well in any way, or is it specifically only a parameter thing?
It's more flexible for data flash log download, but it doesn't actually make it any faster in the tests I've done. Basically, our log download was already reasonably well pipelined, had large blocks. It already was doing all the things we've done on FTP. And so it was a reasonably efficient protocol already. Whereas so it's not a big improvement. It's like maybe 3% improvement of the tests I did, so it's barely worth doing, and it's really within the noise. Where we'll really get a big big download speed improvement is when we implement the fast USB, and we've got the first piece of hardware that supports that that came out just a couple of months ago in prototypes. The CUAV NORA board supports the high-speed USB option, which should be able to give us an order of magnitude faster USB support. But I haven't done the integration work, and there's a lot of low-level system work to do to support that. So as yet, it's just running at the same speed of USB as our existing one. But I do hope that in the future, we'll see more boards come out with that high-speed USB once we've got the software support for it. All right, so that's our parameter file system, and I think that's going to make a big usability, particularly on radio links. Huge difference also on Wi-Fi links. It reduces the time on Wi-Fi very similarly to USB. All right, this next one is one that I actually coded this morning, woke up a little bit early and thought, well, I'll throw in an extra feature for the talk. And it's something that I discussed a bit on one of the dev calls a while ago, but hadn't implemented. And this is a sys file system. And basically, this is a file system prefixed with @sys that allows us to present arbitrary text or binary data using a simple API in the code to present that as a file without it touching the SD card. And so the example that I've implemented this morning is a @sys threads.txt. And what that does is that gives you a real-time monitoring of what threads are running, how much stack each thread is using, what the priority of each thread is. So I can demonstrate that. And I'll just fetch the threads.txt to minus. And you can see there that, so if I update that, it'll update the priorities, etc., as it's running, and update the stack usage. And we could have CPU usage and other things coming out there. So this one is quite useful for debugging, actually. So you can see how close you are to running out of stack per thread. But really, I did it as an example because what I'd like to do is present things like the CAN DNA database. So you'll be able to do, for example, DNA.txt to get the list of CAN nodes and their node name and perhaps the version number and git hash and other things out of the CAN DNA database. Maybe get things like internal information from, say, the optical flow image, the latest, flow image, or fetch things like bulk data out of our avoidance algorithms, which we often have some bulk data that's hard to represent in Mavlink, and this gives us an alternative way to represent that data as a file system. So I'll just show you how easy that is to do. So in this particular case, I just added this function called thread info, which is, it just takes a buffer and a buff size, and you just write into that buffer, and that's immediately presented as a file. So it's very, very easy here. So to add in a particular one, it's not done as a switch statement yet. It's just a little if statement. If they're asking for threads.txt, we just go and ask hal util thread info, and there we have it, the threads information displayed back to the user. So this is going to be an extremely flexible way of presenting bulk data to users via FTP. Any questions on that at all?
I just want to say it's really cool, super cool. And I was just wondering, for example, we had this issue, you know, last year with this project where we were collecting mapping data from a from an underwater sonar, and it came up with a ton of data, more than that I was really comfortable to stick into the data flash logs, because you just blow out the log size, and I wasn't sure, you know, if we could store that much data in the logs, you know. Or I wasn't sure how much time it would take to store it in the data flash logs. But, you know, I guess we could put that kind of ad hoc data in there as well, into these files?
We could. If it's bulk data, sort of megabytes of stuff, and if it's streaming and updating all the time, you're probably better off putting it on the FTP card for review later. But this is better for sort of debug data, stuff that's live, that the user wants to be able to view. And the idea is that the ground station can then present this. For example, I could imagine that Michael could add a, you know, under the Control F window, have a magic key to show all the stack information. And that way, if you ever suspect that maybe I've got a problem running low on stack, or I wonder what I've done on this board, you can just go and press that magic button in Mission Planner and get an instant display of the stack usage and stack remaining for each thread. Because previously we had to recompile ArduPilot to enable that support. And now we can just have it built in and available. Profiling as well. I'd like to present all our profiling counters as a profiles.txt to be able to get profiling information on where our CPU time is going. There's a lot of stuff I think we'll be able to present here. And it's really, you know, some of it will just be for developers, but some of it I think will be actually quite useful for end users, particularly things like the CAN database device list of all of the devices, I2C, SPI devices that we've got, how many transactions they're doing, how many errors they've had, that type of thing. So similar to what you would get sysfs in Linux.
I think a prime candidate for this is like Shutter timestamps. A lot of people like to do that for PPK and whatnot.
You could indeed. Yeah. So lots of things you can do there. There's one also, a cool one that I forgot to show earlier when I was showing the ROMFS. Because we've got this ROMFS, which is just a compressed file system, and just make that a bit bigger for you. It's just a compressed file system of data from compile time. What I've done is I've made it automatically gather the hwdef.dat from the build, which is the definitions for the board. And you can go and fetch that like this. So there's the hwdef.dat from the cube black. Notice it decodes the includes and sort of linearizes it into a single file. The reason that's useful is we've had a problem sometimes with vendors who make like a commercial quadcopter without really talking to the ArduPilot dev team. Then they release it, but our community wants to be able to hack on it. But they can't really start hacking on it without knowing what the pinout is on the vehicle. So now, as long as they're based on a version of the code that's had this patch in it, any user will be able to fetch the pinout of the vehicle along with all of the assignments, the sensors, etc., which means they will be able to rebuild the firmware themselves and upgrade these proprietary vehicles, which could be really cool for some of the little tiny quadcopters that have been coming out of China that haven't played by the rules and given us access to their source code. So I think that'll be quite a useful feature. In some ways, it's cheating. You know, the reverse engineering task to work out the pinout can be quite fun, but this is sort of cheating. You get the instant access to the complete set of defines for the vehicle. So any questions about AP file system before I move on? All right. So the next big change in the last year was the Watchdog system. And this was prompted by a flyaway that we had actually here in Canberra, and where we locked up, and the vehicle, a fixed wing, was so perfectly balanced it kept flying for a long time. So we now have this Watchdog system. Many of you would have seen videos and things about it and how it works, but you may not have seen the WDOG message. The WDOG message, we've been enhancing that lately. And in fact, Peter's added another enhancement to it just recently, which is really useful. This basically gives us a lot of information about what happened. And this allows us, in many cases, to diagnose the cause of a failure. So the big step forward with Watchdog is previously we had no way to differentiate between a power failure and a software failure. And now we've got a really good way to differentiate the two. And we can not only differentiate when we know it was a software failure, we can very often say what the software failure was based on a flight log. And basically it stashes a little bit of information away during a failure event into some persistent memory, which after the board resets itself, it automatically logs that information. And that's been incredibly useful to, for diagnosing failures. And it's led to a lot of really important bug fixes. You saw many of them yesterday in the talk that Peter presented. It also allows for complete restore of some of the key states. So on a fixed wing vehicle, you can get a Watchdog and a complete reboot due to a software failure and then keep flying. And there's a lovely demonstration video by Marco of that, where you can you know, reboot in flight and then continue flying, even rearm the vehicle and come back and land after a complete failure. All right, so Compass improvements. There's been a huge number of Compass improvements in the last year. A lot of them thanks to Sid and to Michael. So Michael O'Born and Sid. We have a new Compass ID system that was merged quite recently, which basically gives us a much more flexible way of dealing with compasses. So it allows us to reorder our compasses in terms of, you know, which one is the primary, secondary, third, and you can probe up to 8 compasses and then specify which of the 3 are actually going to be activated. And it is very smart in terms of sorting those devices, and it gives the ability for ground stations to make a nice user interface like this one that Mission Planner has done, where you can basically sort your compasses much like you do, say, a mission item. And that's incredibly powerful because people have, compasses have been a major pain in terms of configuring vehicles, particularly when they're on a detachable bus like I2C or UAV can. And this just offers a lot more flexibility in configuring the priorities. So many thanks to Sid for a huge amount of effort that went into that. As Paul mentioned, we've got the new use of the World Magnetic Model, which is being used in a whole bunch of places now to allow for much more robust mag fusion. And it's also used in Compass, with Compass calibration to automatically calculate a scale factor, which is really important for some compasses that may not have a unitary scale factor. And it allows us also, it's a good validation point that the compass is working as expected within the World Magnetic Model. So that's come in quite recently and has gone out into our stable releases. The new Compass ID system we expect to go into the next stable release. So finally, we've got some new filtering options, and Leonard has already mentioned these, and these are really a huge improvement. Massive thanks to Andy and Bill and to Leonard for their work on these new filtering capabilities. And I was really quite surprised at how well this works, even on our lowest end CPUs like the F405 on many of the little small racing boards. Real-time FFT support allows us to automatically find the peak of oscillation and then automatically shift our harmonic notch filter to be centered around that peak, which just makes a massive difference in filtering out the oscillation due to the motors and allows you to get much better tuning, basically allowing you to have higher D terms, which gives you much better disturbance rejection and really a much better tune. So fantastic work by Andy, Bill and Leonard on that. So we've got a lot of driver changes in the last year. And so I summarize those, each month at our monthly partners meeting, and there's really sort of 20 or 30 each month typically, but I've just put up some of the highlights of the last year. So moving baseline support for GPS is really important for people with, particularly large industrial vehicles that might be operating in areas with very poor magnetic fields, where they might be close to, say, a boat or a building or a chimney stack, like Paul pointed out before. So we can now use 2 GPSs and set them up as moving baseline RTK and get a reliable yaw estimate from the dual GPS. And that in tests that have been done so far, it looks like it's performing very nicely. WS2812 LEDs, we can now do a lot of things with those, and there's some vehicles that have come out. There's one with 63 LEDs in a lovely pattern on the arms for a light show vehicle, which I was really delighted to see. And we've had also Peter Hall doing some really fancy thing with the LED APIs. All of those supported by Lua scripting for controlling the pattern of LEDs to allow the pattern to reflect the vehicle's state. EFI support is another important one for really big vehicles. So we now support electronic fuel injection systems like the Mega Squirt and others. And that allows us to monitor things like the cylinder head temperature and the oil temperature and gas pressures, all sorts of things about the EFI, which is very important for monitoring the very long endurance UAVs that might be up there for, say, 16, 20 hours. And monitoring the health of the engine is extremely important when it's a beyond visual range vehicle. So it's great to get support for all that monitoring happening in ArduPilot. F-port was something we've been asked for several years, and we finally got implemented. And we'll be having Yapu talking in more details about F-port later. Basically, it's a one-wire RC and telemetry system, so single signal wire, bidirectional, giving you robust RC input as well as good telemetry down to your transmitter for displaying even things like a moving map and attitude and all sorts of other information. We've got a new InventSense API supported, thanks to Sid, for the newer InventSense IMUs, which provide much better sampling and better filtering options. So really great support on that by Sid. Thank you very much. New CAN rangefinders are now supported, and they're supported within AP Periph. It's very handy to be able to take one of the existing serial rangefinders, like the Lightwear ones, and convert them into CAN rangefinders using the AP Periph CAN nodes. And finally, RunCam support. There's people who've been asking for that for years, and Andy Piper's done a really nice job on RunCam support, including runtime configuration of the camera. So there's sort of some key changes in the last year, but there's been a lot of others. A little bit of planned work for the next year. So we've had, we're hoping to get FD-CAN support. So Sid has put his hand up for that, which will allow up to 8 megabyte data on CAN on the H7 chips. And we'll need also support for FD-CAN peripherals. I'm really looking forward to that because it's going to give us, a lot more bandwidth and be allowed to support a lot more CAN devices. So I think we're going to be transitioning across to FD-CAN over the next few years. Bidirectional D-shot for very fast RPM feedback. It means you can get RPM feedback from all of your motors individually at rates of several hundred hertz. We don't have that yet, but I'd like to implement that soon. It's a very clever protocol. We've had a number of performance regressions over the past 6 months or so, and I've spent a few days looking into those and got some ideas how to fix them, but that hasn't happened yet. So for those of you who notice that our scheduling misses rate has gone up a bit in the past 6 months, there is work being done to try to fix that. So DMA contention improvements, we've got some issues at the moment where we have contention for a single DMA channel for multiple peripherals, particularly affects things like, people who are doing, say, 4 or 6 channel D-shot, and they've got overlapping DMA channels for those different D-shot outputs. You can get missing frames on D-shot. So that's an important improvement that's coming soon. And fast USB support that I mentioned earlier, thanks to the CUAV NORA, looking forward to supporting that for much faster log download, I hope. So that's about it for the systems update for March 2020. So any questions?
Rich, a quick question
Yes, Louis.
regarding the support of the newer CPUs with the F7 and H7.
Yep.
Do you have anything planned to support specific issues, specific features of these new CPUs, like the new H7s that have multiple cores?
We haven't. I've sort of scoped out what would be involved in multi-core, but we haven't actually implemented that yet. It's a big job, and I'm not sure it's worth it. So I'm not sure why my Skype display is getting wrong, but anyway. So the adding support for multi-core it's a huge amount of work at the Shibios level, and the benefits are not really clear, and whether the benefit is worth it at this stage, particularly as now we've gone to H7. I mean, the only ones that support it are the newer H7s, and it's not supported by the H7s we support at the moment. It's the next generation of H7 that can support it. I think it will happen, but I don't think it's going to happen in the next year. It might be the year after. And I'd rather let the rest of the Shibios community lead on that one, because it's probably several months' work. And I just think the benefits to us at the moment, we're not CPU constrained on H7 at all. We tend to have lots of spare CPU. So I'd rather wait until we become CPU constrained before I put several months of effort into multi-core support.
And about the other features that both the F7 and H7 support and the F4s don't support.
So no, I mean, there are various sort of there are various CPUs that ST has which have multi-core where they're not symmetric. So there's sort of asymmetric cores where they might have an M4 and an M7. That's a difficult thing to use inside ArduPilot. It's possible, but I struggle really to see the benefit. And as yet, for our project, I don't think the effort to support those chips is worth it right now. If somebody comes up with a compelling argument why it'd be a massive advantage for a significant part of our community, then I'd be happy to put the effort in. But I've worked a lot on multi-core operating systems before, and I know just how many months of effort it takes to get that right. I mean, it's sort of easy to do it badly, but you don't see a real benefit if you do it badly. To actually do it well with the fine-grained locking that you need, it's a huge task, and it's fraught with race conditions. So it's not something that's really on my roadmap for the next year.
Now, Dridge, how does that relate to your Snapdragon work, where you had the asynchronous cores on the DSP?
Yeah, but that was they were basically running an RTOS that already supported multi-core. So we did 2 ports to the Snapdragon. We did one on the Linux ARM cores and the other to the DSP cores. In both cases, the underlying RTOS already had full multi-core support, and we'll be just treating it as a multi-threaded RTOS, which is absolutely fine. So the hard work isn't in the ArduPilot layer. The hard work is in the Shibios and the HAL. And as yet, Shibios doesn't support those multi-cores on STM32. So I'm reluctant to jump in and do that work myself without a compelling reason to do it. We obviously support multi-core already on the Raspberry Pis. I mean, people fly Raspberry Pis with ArduPilot all the time, and those work absolutely fine multi-core. But and there's no problem because ArduPilot supports it fine. We've got all the locking primitives and things. It's the RTOS layer that's the hard bit in Shibios for that.
Gotcha, understood. Makes sense. My next question is FD-CAN that Sid has jumped on. Do we have any hardware that's going to support that in the future, like in the queue? Like, does the H7 support that?
So H7 does support FD-CAN, yes. So if you build an H7-based peripheral, then you'll automatically get FD-CAN. In fact, we already support FD-CAN running in legacy CAN mode. So if you've got an H7-based board like a Cube Orange or a Durandal, then you're already using FDCAN, in fact. You're just using it in a legacy mode where it's backwards compatible with the 1 megabit CAN. And that was what was implemented by Sid originally when he added support for the H7 CAN.
Great.
The next trick is to support FDCAN in native FDCAN mode, which gives you it's still got 1 megabit framing, but it's got 8 megabit data packets, and it's got much larger packets, which means the overall bandwidth you get is enormously higher. So it's sort of 10 or 12 times higher. It's more than 8 times higher because the larger packet size means the overhead is considerably less. So it's going to be a huge improvement in bandwidth.
So basically, it sounds like Sid knows what he's doing.
Sid knows what he's doing. The trick will be the peripherals, because the microcontrollers that support FDCAN, currently the only one we support is the H7. And the H7 is quite an expensive microprocessor at this stage, which means putting it on a peripheral, you'd want it on a high-end peripheral. So a high-end GPS, if you're aiming a GPS at a price point of sort of $500 plus, you could happily have an H7 on the GPS to do the FDCAN. But a GPS doesn't need a lot of bandwidth, so it's not the one that really needs it.
Yeah.
The trick
whether
will
we
be doing the low-end peripherals with FDCAN, and that will probably mean an external FDCAN adapter, which we haven't done yet.
right, because there are, I'm pretty sure there's 0 devices. I'm sorry, 0 F4 devices that have it. Do we know if there's any?
You'd have to have an
F7?
external. You can go and buy little FDCAN adapters for SPI, and you could happily attach those on SPI to your F4, and that would give you FDCAN on F4. We just need to write a device driver for CAN connected via SPI, which is not all that difficult to do. We just haven't prototyped that, and really the thing that's lacking is the 1 megabit CAN is working good enough for us now. And so there hasn't been a lot of effort put in to do the FDCAN. So I was delighted that Sid put his hand up to say that he's going to start putting that effort in soon, because that'll prepare the way for when we really do want more bandwidth, which will be for things like the scanning laser rangefinders, say the spherical scanning laser rangefinders, might come in over CAN and use a huge amount of bandwidth, or other image devices that come in, high-end optical flow sensors, something like that.
Sure, or external IMUs and such.
Exactly, yeah, that sort of thing, where you start filling up the CAN bus fairly quickly, particularly really high rate IMUs.
Wish I had that a couple of years ago.
Any other questions? All right, so we might close that talk there then. We're only a little bit over time, so we're not doing too badly on the schedule.